Hello dear students, I hope you are good, I hope you are safe. As far as your studies are concerned about physics, we were doing chapter number 9, ray optics. Today it is going to be the ninth part of the lecture series. Till now we have discussed refraction through spherical surfaces and we have solved some numericals also. Today we are going to solve some more numericals and then after we are going to do the lens maker's formula. But before doing lens maker's formula, a short introduction of lenses will be there. Okay, so let us start and let us do the one or two numericals on the basis of refraction through spherical surfaces. In the last video lecture we have discussed some numericals. Today also we are going to discuss one more only so that we can cope up with the concept. Moreover, we have done a numerical on which the mark was here, means object is here. In another question object is here. One question can be made when the object is here. Now I am going to take object outside the sphere. Okay, so suppose somewhere here the object is O. It is center, so it is given that CO is equal to 30 centimeter, whereas radius of curvature is 10 centimeter. Question is, where will be the image, or we can say the apparent position, where will be the apparent position of O if it is viewed from this side, obviously. Okay, so again from O one ray goes straight along the axis only. It will pass without deviation and it will go like this. Okay, another ray, it will strike somewhere here. Now what happens? Refraction will take place, and in refraction what happens? Now since the ray of light is going from rarer to denser medium, the ray of light must bend towards the normal. So this is our normal. So ray of light must bend downward, okay, towards the normal. So how the ray of light goes? So ray of light goes like this. Okay, ray of light goes like this. And if again it strikes on this surface, so again what happens? Now it is going from denser medium to rarer medium, so it will bend away from the normal. So ray of light must go this way, and somewhere here the final image will be formed, and this will be the apparent position. Okay, but if we extend this one, the refracted ray from the first surface, it will cut the first refracted surface somewhere here. Let this be the I dash. Okay, I dash is the image formed by the first surface. I dash is the image formed by the first surface. So this is how the ray diagram is. Now we have to remember one thing. Whenever a refraction or reflection more than one surface is involved, like here refraction is taking place two times, one from this surface, another from this surface. So basically what happens, whenever refraction takes place from two different surfaces, you need to understand that the image formed by the first surface will act as an object for the second surface. This is the key point, and it will be with us till the end of the chapter. The image formed by the first surface will act as an object for the second surface. So basically this I dash is going to act as an object for this refraction. Okay, so let us first of all try to find out where is the position of I. Let this point be P1, and we have to find all the positions with respect to P1 for first refraction. For first refraction For first refraction, say this is your mu1, this is your mu2, this is your mu1. Okay, so first refraction, refractive index of second medium. Here the refractive index is 1, its refractive index is 3 by 2 or 1.5. The refractive index of second medium is 1.5 for the first surface upon image distance, minus refractive index of the first medium, it is 1 upon object distance. Object distance will be measured from P1 to O. Now just see, CO is given 30 centimeter and CP1 will be the radius of curvature, it is 10. So from P1 to O it is 20. So it will be minus 20. Why is it so? Because we are moving this side, is equal to refractive index of second minus refractive index of first upon radius of curvature. Radius of curvature for P1 to C, we are going that side, so it should be positive. It should be plus 10. Okay. Now if we solve it, we are going to have 1.5 upon V is equal to, this is transferred that side, minus and minus will become plus. If it is transferred that side, again it will become minus. 1.5 minus 1, it is 0.5 upon 10 minus 1 upon 20. Okay, 0.5 upon 10 minus 1 upon 20. So it will be like 1.5 upon V is equal to, LCM will be 20. It will be 1 minus 1. Answer is 0. So 1.5 upon V is equal to 0. So V is going to be what? Infinity. So basically there will be a change in ray diagram. Okay, what I thought that ray should bend this much, the image is formed at that point, but in reality from the mathematical calculation we come to know that the ray of light bends in such a manner that it cuts the principal axis at infinity. So now what will happen? The ray diagram will be changed a bit, and how much it will be changed? Just see. From this refraction, what happens? This ray of light becomes parallel to the axis. So basically, when it is extended, it cut this axis at infinity. Okay, that is why the image is at infinity. Now what will happen? Again at this point, the refraction takes place. So if the refraction takes place, it will be bending toward away from the normal. So ray of light will go somewhere here and find the final image, right? So basically what happens? From the first phase, since V is infinity, for the first phase image is at infinite. So ray of light becomes parallel to the axis, and after getting refracted from this surface, it bends at this point. Now for second refraction, for second refraction, say this is our pole, all the distances will be measured from pole only. Ray of light is moving from this medium to this medium, so this medium is going to be our second medium and 1.5 is going to be our first medium. mu1 is 1, it is here. So basically 1 upon image distance minus refractive index of first medium upon object distance. Since object is at infinity, because image formed by this surface is at infinite, so basically object distance is going to be infinite, is equal to refractive index of second medium minus refractive index of first medium upon radius of curvature. Radius of curvature P2C, it is negative, so it will be like minus 10. So this will go to 0. 1 upon V is equal to minus 0.5 upon minus 10. Minus and minus will be cancelled out. So V is going to be what? 20 centimeters. Since it is positive, so basically P2I, this distance is what? 20 centimeter. If from the center it is being asked, then from the center to P2 it is 10, P2 to I it is 20. So from the center it is 30 centimeter. So this is how we solve the question. Okay, luckily we get infinity over here, and this makes the solution very easy. If it would have been some value, we have to put that value here and we have to solve accordingly. So these kind of questions are solved like this. Okay, I hope you are able to do. One more thing can be done, that this glass sphere can be immersed in water. So in that case, what will happen? In case of we have taken refractive index as 1, in place of 1 you have to take refractive index of water. Refractive index of water is 1.33 or 4 upon 3. You put the values and get the result. Okay, what can be done? The refractive index of the surrounding medium can be changed. Okay, so this can be done, I think, very easily. Okay, so this is how we solve these type of questions. Okay, I hope from these last 2-3 examples you are able to understand how we solve these kind of questions. Now we have to apply this formula, the refraction through spherical surfaces, to prove lens maker's formula. But before doing lens maker's formula, let us have a short introduction of lens. Lens. First of all, what is a lens? I hope you must have studied in class 10th. You have seen this lens. This lens is called convex lens. The full name of the lens is not convex, actually it is biconvex lens. Okay, you must have seen this one also. This is concave lens. This is concave lens. Okay, the thing is, and other type of lenses are also can be made, like if one surface is plane, so it will be plano-convex lens. If one surface is concave and one surface is plane, so the lens will be plano-concave lens. It is plano-convex, it is plano-concave. Other lenses can be made like this. If the lens is like this, so it is called concavo-convex. Concavo-convex. And this lens is called, this is called convexo-concave. Okay, this is biconvex lens. Biconvex, it is biconcave. Why it is called so? Because bi means 2, concave means both the surfaces are concave. Biconvex, bi means 2, both the surfaces are convex. It is plano-convex. Plano-convex. It is plano-concave. Plano-concave. It is convexo-concave. Sorry, concavo-convex. Concavo-convex. And it is convexo-concave. In some books it is written as positive meniscus. Positive meniscus, and it is written as negative meniscus. Why is it so? Because it is a kind of converging lens and it is a kind of diverging lens. So these are the type of lenses, but again the thing remains there only. What is a lens? What is the definition of lens? So definition of lens is given as a homogeneous medium, a medium which is uniform by mass distribution and everything, a homogeneous medium bounded by homogeneous transparent medium bounded by at least one spherical surface or cylindrical surface is called a lens. The other surface may be plane, may be spherical, may be cylindrical. Is it clear? So definition of lens is going to be a homogeneous transparent medium bounded by at least one spherical surface. Other may be plane, other may be cylindrical, is called a lens. Okay, is called a lens. And these are the type of lenses you already know. Okay, this is called biconvex, biconcave. If both the radius of curvature, because this surface, for this surface, both the surfaces are convex, both the surfaces can have different radii of curvatures, they may have same radii of curvature also. So if the radii of curvature is same, it is called equiconvex lens. It is called equiconcave lens. Okay, equiconvex and equiconcave. So these are the type of lenses. Okay, now we are going to study lens maker's formula. Okay, why the lens maker's formula is called so? Because what happens, the lens manufacturers, they use this formula to know the required radius of curvature to make a lens of desired focal length. Okay, so basically this is a formula which relates the refractive index of the material of the lens with the surrounding and the radius of curvature and the focal length of the lens. Okay, so we are going to study lens maker's formula. After that we'll have a small introduction about focus, focal length and everything. Okay, but for focus I must say that focal length is defined as the distance from the optical center of the lens at which an image is formed if the incident rays are parallel to the principal axis. Okay, if the rays are coming parallel to the principal axis after getting refracted from the lens, if this is a convex lens, first of all we should know what is focus, what is focal length. If rays are coming parallel to the principal axis, then after getting refracted from the lens, they pass through a common point on the principal axis. Okay, so from the optical center to the focus, this length is called focal length. Okay, so this is the focal length of convex lens. And for concave lens, how the focal length is given? So focal length is given something like this. If rays of light are coming parallel to the principal axis, after getting refracted from the lens, they pass through, they actually diverge. But when we extend the divergent rays, they appear to pass through a common point. So this time the focal length is somewhere this side, from the optical center to that common point. Okay, so this is called focal length, and we use this definition to find lens maker's formula. When the object is at infinity, then the rays coming parallel to the principal axis. So basically when the object is at infinite, the image is formed at focus. Okay, so we use this particular definition that when the object is at infinity, the image formed is at focus. We are going to use this to prove lens maker's formula. Okay, let us try to do that. Okay, let us make a convex lens to understand. Say this is your convex lens, biconvex lens. Okay, and this is its principal axis. Now what happens? From here, say this is our object O. From the object, one ray goes along the principal axis and goes like this only. Okay, another ray falls on this surface. Now what happens? Ray of light is going from rarer medium to denser medium, so it should bend towards the normal. Where is the normal? So for this surface, spheres will be completed something like this. Center will be somewhere here. So this is your center of curvature C1 for this surface. So normal will be drawn like this. So this is going to be act as normal. So ray of light, what happens? Ray of light will bend. So this is the original path of the ray. This is the original path of the ray. It will bend towards the normal. So ray of light will bend like this. Okay, and when we extend this ray, it will cut the principal axis at this point. Let this point be I dash. Okay, but what happens before cutting at I dash? It strikes at the second surface, and on the second surface again the refraction will take place. For this surface, sphere will be completed like this. So center of curvature will somewhere be here. So from the center of curvature, if you draw a normal, the normal will be something like this. Now this dotted line represents the original path of the ray. it will bend away from the normal as it is moving from denser medium to rarer medium. So the light will bend somewhere here. So here the final image I will be formed. Okay. Now let us describe the distances. For the first surface, let this be pole. For the second surface, let this be P2. Okay, sign convention remains same. Sign convention is as it was. For the first refraction, for the first refraction, I'm going to apply the refraction through spherical surfaces formula. Say this is your mu1, lens medium is mu2, and this is your mu1. Okay. Now for the first surface, just see refractive index of second medium, which is mu2 upon image distance. Where is the image distance for the first surface? It is P1 I dash. I dash is the image formed by the first surface. So it will be P1 I dash minus refractive index of the first medium, it is mu1, upon object distance, it is P1O, is equal to refractive index of second medium minus refractive index of first medium upon radius of curvature. Radius of curvature is P1C1. P1C1. Let this be equation number 1. Okay. For second surface, for the second refraction, for the second refraction, for the second surface, this is going to be the surface, this is our pole, all the distances will be measured from pole only. From pole, where is the object? I dash is the image formed by the first surface, so it will act as an object for the second surface. So P2 I dash is going to be our object distance, P2 I is going to be our image distance. So let us try to write the equation. Now the ray of light is going from mu2 to mu1, so mu1 will be acting as our second surface. So formula, according to the formula, refractive index of second medium, which is mu1, upon refractive index, image distance. Where is the image distance? It is P2I. P2I minus refractive index of first medium. Refractive index of first medium is mu2 upon object distance. Object distance is P2I dash. P2I dash is equal to, now mu1 refractive index of second medium minus refractive index of first medium, which is mu2, upon radius of curvature. For the second surface, radius of curvature is P2 C2. It is C2. So it will be P2 C2. Now I'm going to change or going to modify this equation. This P from here till here, P2I dash, P2I dash. It can be written as P1I dash minus P1 P2. From P1 I dash minus P1 P2, we'll left with this one, which is P2 I dash. So I'm going to change that. It will be like mu1 upon P2I minus mu2 upon P1 I dash minus P1 P2 is equal to what? Mu1 minus mu2 upon P2 C2. Okay. Now just see, lens maker's formula is given for thin lenses. In the very beginning of this chapter, I have told you that all the apertures, the thickness of the lens and mirrors are neglected. Okay, because they are very small comparison to the other distances. So basically this P1 P2 is very small in comparison to P1 I dash. So we'll write that since P1 P2, which is thickness actually, it is very smaller than P1 I dash, so it will be neglected. So therefore we'll have mu1 upon P2I, mu1 upon P2I minus mu2 upon, now P1 P2 is neglected, we are left with P1 I dash. P1 I dash is equal to mu1 minus mu2 upon P2 C2. This is the equation we are left with. Let this be equation number 2. Now what I am going to do, I am going to add equation number 1 and equation number 2. Then equation number 1, it is mu 2 upon p1 I dash is positive. In equation number 2, mu 2 upon p1 I dash is negative. So when we add them, it will become 0. So what we are left with, mu 1 upon p2i, which is positive. Equation number 1 is added with equation number 2. So I am going to have with mu 1 upon p2i minus mu 1 upon p1o. Mu 1 upon p1o is equal to, now just see the right hand side, mu 2 minus mu 1 upon p1 c1, mu 1 minus mu 2 upon p2 c2. What I am going to take, I am going to take mu 2 minus mu 1 as common. So I am going to left with 1 upon p1 c1 minus 1 upon p2 c2. This negative sign is there because it is mu 1 minus mu 2 and I have taken mu 2 minus mu 1 as common. Okay. Now mu 1 is transferred to that side. So it will be like 1 upon p2i minus 1 upon p1o is equal to, now mu 1 is divided over here. So mu 2 upon mu 1, it will be what? Mu 2 1 minus mu 1 upon mu 1, it will be 1. 1 upon p1 c1 minus 1 upon p2 c2. Okay. So this is the equation we are left with now. Now just see how this equation has come. Are you able to understand? Like mu 2 minus mu 1 upon mu 1 is there. So it is divided. Mu 1 is transferred this side. We'll get this one. So it can be written as mu 2 upon mu 1 minus mu 1 upon mu 1. So mu 2 upon mu 1, it is mu 2 1. Mu 1 upon mu 1, it is 1. So we are left with this one. Now just see P2i. P2i is the final image distance, but it is from this surface. All the distances in case of lenses, they are measured from the optical center. Optical center for a convex lens, it is midpoint. It is midpoint. Since P1, P2 is very small, so P2 and this midpoint is distance is going to be also very small. So whether we measure it from P2 or whether we measure it from optical center, they'll be approximately equal because the lens is very thin. So basically P2i is our image distance and it can be written as 1 upon V minus P1o. It is the object distance from P1. Again it can be considered as object distance from the center. So it will be 1 upon U. Here it is mu 2 1 minus 1. 1 upon P1 C1, it is the radius of curvature for the first surface minus 1 upon radius of curvature of the second surface. Okay, let this be equation number 3. Now one confusion can be there. Why I have not kept with the sign convention? Sign convention I have not used, if you can see. Why I have not used? Because if I use sign convention, it is going to be proved for this particular lens only. So basically I am not going to use it sign convention, and when we put the formula for different kind of lenses, then I will be putting with sign convention. Okay. Now here one thing is there, by basic definition of focus, if object is at infinity, the image must be formed at focus. If object distance is infinity, the image must be formed at focus. So if we put this value over here, we'll get 1 upon f minus 1 upon infinity is equal to mu 2 1 minus 1, 1 upon r1 minus 1 upon r2. So basically 1 upon infinity becomes 0. And what we are going to have with? We are going to have 1 upon f is equal to mu 2 1 minus 1, 1 upon r1 minus 1 upon r2. This formula, the last equation, which is equation number 4, is called lens maker's formula. Equation number 4. It relates focal length of the lens and radius of curvature of both the surfaces. This is called lens maker's formula. This is the formula used by the manufacturers to find the required radius of curvature for a desired focal length. Okay. One more very important equation we get from here. If we compare equation number 3 and equation number 4, from 3 and 4, then what we are going to have? Just see equation number 3, right hand side, equation number 4, right hand side, both are same. So left hand side should also be same. So we can write 1 upon f is equal to 1 upon v minus 1 upon u. This is called thin lens formula. thin lens formula. And equation number 4 is called lens maker's formula. This derivation is very important with respect to your exams, with respect to your knowledge also. Okay, this derivation is very important because this derivation tell us how this equation has come for a thin lens, how lens maker's formula is being derived, and now lens maker formula is applied to various lenses, for plano convex, for concavo convex, for biconvex, for equiconvex, for every kind of lens this formula can be applied. Is it clear? So you need to understand the derivation, you need to understand the basic steps what I have taken to prove this formula. Okay, so this is lens maker formula and it is very important. What you need to do, you need to prepare lens maker's formula in a very detailed manner, and it is very important, as I have told you, in respect to your board examination also. Okay, just pause the screen and just note it down, all the derivation with the ray diagram. I hope ray diagram is clear. This is all for the day. This is all for the day. In the next video lecture, we are going to understand how this lens maker's formula is being applied to different kind of lenses. Okay, thank you all of you.